Okay, so if we're going to determine the molar mass of some compound, the first equation that comes to mind is the definition of molar mass. I call it molecular weight, but it's the same thing. We need to know the mass, right? Mass for a certain number of moles of a compound, right? So in our experiment, we find out what is the freezing point for the solvent. So we do the solvent freezing point. And in order to get that, we have time versus temperature. So over a period of time, temperature changes and we melt it first. Right? So we're actually watching as it goes from a liquid to a solid. So over a period of time, it changes here. And then for simplicity's sake, once this temperature stabilizes for 3 in a row, then that's your freezing point. What you may notice is it'll get down to a certain, it'll decrease, decrease, decrease. And then maybe for a couple of them, it'll be constant, and then it'll jump back up and then back down and stabilize, right? If it does that, that's called the latent heat of fusion. When something goes from a liquid to a solid, it gives up heat, right? It's an exothermic process. So what it may do is jump the temperature up as it goes from the liquid to the solid, and then it's stabilized. So we find the freezing point for the solvent, and then we find the freezing point for the mixture. Right. Same thing. Okay. So you find a freezing point here, and you say, what's the difference? And we don't care if it's positive or negative. We just want the absolute. Okay. Then that's going to be equal to the Van Hoff correction factor times the K freezing point for the solvent. And what's our solvent in this case? Lauric acid, right? Lauric acid. For our solvent, lauric acid. Times the molality of the solute. Okay? So once we find this value, and the Van Hoff correction factor is going to be what? Does our solute dissociate in solution? No, it doesn't. It stays molecular. So Van Hoff is 1. You don't even have to consider it. And then the K for the solvent is given in the pre-lab section as 3.90. So this is 3.90. It says degrees C kilogram mole. That's the same thing as degrees C per molal. Okay, so if we find out what this is, and we know what that is, we can calculate the molality of the solute. Okay, once you know the molality, what's the molality? Molality is mass. Excuse me, no, not mass. It's moles. Moles of solute per kilogram of solvent. Right? That's molality. So once you determine the molality, you can come over here and say, all right, I've got this value from there. I've got this value because when we made up the solution, right? When we made up the solution, we had so many grams of our solvent, right? So you just have to convert it to kilograms and plug those in. Plug this one in, plug this one in, solve for that one. Now you have moles. where you get the mass. When you made up the solution, you have two masses, solute and solvent. So then all you have to do is plug in the mass for the solute and you calculate the molecular weight, the molar mass. Okay. So let's go to the pre-lab question. 7.98 grams of lauric acid froze at 43.75. So 7.98 grams of lauric acid at a freezing point of 43.75. And then when you add 1.03 grams of benzoic acid, the freezing point changed. $39.43. Okay, so we see that there's a depression in the freezing point by adding that solvent, solute. Okay, so what's delta T? Well, absolute delta T. We could say, I'm sorry?
You subtract them?
Yeah.
Temperatures?
3. Got 2, 3, 4?
Yeah.
4.32? And we,
That's what I got.
yeah. 4.32 degrees C equals, and then the K for this is given as 3.90. 3.90 degrees C kilograms per mole. And then the molality is are unknown. So to find the molality, we just divide this one by that one. This is degrees C, kilograms per mole. And what do we get?
I got 1.1077.
1.1077. And that, this is canceled, so this would be moles per kilogram. Okay, now we know that. If this is 1.1077 moles of benzoic acid per kilogram of lauric acid. Okay. Now all we have to do is multiply that times how many kilograms of lauric acid is it? Well, 7.98 grams is 7.98 thousandths of 7.98 times 10 to the minus 3 kilograms of lauric acid. Okay. So now what do we get?
I got, which I didn't, I wrote it out as 0.00798, but 0.00884. Sound right?
884. And how many zeros in front?
2, not counting one before the decimal.
Times 10 to the minus 3.
Yeah.
That's reasonable. Yeah, 1.1 times that. Okay. And this is moles of benzoic acid. So now we can calculate the molar mass with 1.03 grams per how many moles? 8.84 times 10 to the minus 3 moles. So divide that number into 1.03 and see what we get.
116.6
grams per mole. Okay. That's how you do it. And that's exactly the set of calculations you're gonna do with the data you acquire in the lab.